Hello everybody, welcome to the stream. I'm going to keep an eye on the live chat. Lots of questions to go through today. We want to do the midterm, but then also some other junk. So, let's go. Midterm. Okay. Question 1. Hold on. Zoom out a little here. Alright, I'm standing on the moon with no air, and I throw the rock straight upwards. Due to the moon's gravity, it begins to accelerate downwards. Circle all the following statements that are false. Before you go anywhere in this, I want to make a note about problem solving in these questions. Moon. So I had a bunch of people ask during the class whether or not I being the person who threw up the rock, I should be included in this question. Technically, I'm in the picture. Look, there I am. But in terms of question problem solving, this question's talking about implicitly, it begins to accelerate downwards. We're talking about its motion after I've thrown it up in the air. So we're talking about its motion after it's left my hand. And so my interactions with it, my history of interacting with it is irrelevant. Once it's left my hand, it does its own thing. The only force between it and the moon is the gravity. Okay, so I'm going to put a check mark before we go on. Let's talk about strategies. How do you solve these questions? One way to do it is to go through it question by statement, asking if it's true or false. So is the system moon rock isolated? Yeah, there's nothing else pushing on it, so that's true. System moon rock is closed. Yeah, it's not really losing energy to anything. System moon rock has two types of energy, kinetic and potential. That's true. System rock has two types of energy, kinetic and potential. The rock alone doesn't have a potential energy because potential energy is all about configuration of stuff inside the system. The rock, its configuration doesn't change its energy. So no, that's false. Total energy of the system rock is constant. No, that's false as well. So if we looked at the system moon rock, yes, that is a constant amount of energy. It's a closed system. But the rock on its own is exchanging energy with the moon. And so the rock on its own, it's not constant. Total momentum of the system is constant. I think that's true. Yeah. So this, once you've gone through and said what's true and what's false, then it's easier to just go, okay, these ones are false. Circle all of the following which describe an inertial reference frame if the origin is my current position. So in other words, this is describing me as a person, what I see, and whether or not I am in an inertial reference frame. Okay, so if I'm sitting in a chair on the ground, that is by definition an inertial reference frame. I'm in an elevator, moving, motion, motion relative to the ground. That's a hallmark of not inertial, but I'm moving at a constant velocity. If I'm moving at a constant velocity relative to an inertial reference frame, then I'm in an inertial reference frame. Downwards constant velocity, same thing. Jump out of an elevator, free fall towards the ground. If I'm in free fall, it means I'm accelerating relative to the ground. And if I'm accelerating relative to the ground, I'm not in an inertial reference frame. I open my parachute and decelerate. Okay, so while I'm decelerating, in other words, first I'm moving fast and then I'm slowing down. If I'm slowing down, it means I'm accelerating and not in an inertial reference frame. I look out the window of my car, several minutes later, I guess. I see objects accelerate even though nothing is touching them, right? So that means I am not in an inertial reference frame. So which ones describe an inertial reference frame? Just this one, and this one, I believe. How do you know this one's not an inertial reference frame? It's because objects are accelerating with nothing touching them. In other words, the law of inertia is being violated, so it's not an inertial reference frame. This one's a cute question. Two carts collide, these two, on a frictionless track. Car A has a velocity blah, car mass blah. Car B has velocity blah and mass blah. And then car B feels a force from car A that looks like this. Draw the force that car A feels from car B. So this is A pushing on B. So this is the force B feels. What force does A feel? It's going to feel an equal and opposite amount of force. I guess I'll write it with red pen. So it's going to look like the mirror image of this. Again, and then back down to 0. That is a go. Let's try this again. I'm just going to freehand it now. There. It's recognizably the mirror image. That's all I need. What's the final momentum of car B? Oh, conservation momentum question. Okay, so initial momentum of car B is 0 because it's not moving. Final momentum. How do I figure that out? Well, if I knew how this one's momentum changed, I could figure out the momentum of this one, right? But it doesn't give me the final velocity of cart A. So I got to use something else. And then I remember the definition of the momentum of the impulse is the rate of change of force. In other words, the area under this graph and the area under this graph tell me how much the momentum has changed by. All right, so what's the area? Let's see. So this has, it's a triangle, so it's 1/2. The base is 1 wide and the height is 2 high. And then this one, the base is 0.5 and the height is 2. And then this one here, the base is 0.5 and it's a triangle and the height is 2. So this term here has area 1 and this term here has area 1 and this term here has area 0.5. So I add them all together and the change in momentum, the impulse is going to be 1 plus 1 plus 0.5. I got that right? Yeah. And so the change in momentum is going to be 2.5. The initial momentum is 0, so the final momentum is J plus Pi, so it's going to be 2.5 kilogram meters per second. Any questions? All right, let's move on to the next one. Two carts moving over a frictionless ground collide and then stick together. The collision described by observer O in terms of velocities shown. So relative to this person sitting still are this one and that one. Okay, what's the velocity after they've stuck together? That's a conservation of momentum question. P total initial is going to be 4 times 5 meters per second plus 8 times minus 1. So this is 20 minus 8. That's 12 kilogram meters per second. And after they collide, it's going to be mass A times final velocity plus mass B. Oh, I guess mb is 8 times final velocity, so it's 12 times the final velocity. We're using the same variable in both these cases because that's traveling at the same velocity because it's stuck together. And so you put these two together. 12 is equal to 12 times v, so v is equal to plus 1.0 meters per second. Relative to this person, how much of the cart's energy, kinetic energy, is turned into heat? All right, so I need to calculate the kinetic energy initially. So it's going to be 1/2 times the mass times the velocity squared plus 1/2 times the mass times the velocity squared. So that's 50 plus 4. Yep. 54 joules initially. Final kinetic energy is 1/2 times the mass times 1 all squared plus 1/2 times the mass times the final velocity all squared. Oh wait, why is it the same? Oh well, I mean you can write in the -1 all squared. The sign goes away. So, all right. So you do this and you get 2 plus 4, 6 joules. So the change in the kinetic energy is 6 minus 54, so that's 48 joules. I think that's right. All right, Carl, C, is riding with velocity v1. What are velocities cart A, cart B, before and after the collision? We'll call it v A initial, v B initial, and v final. We'll call it those things. Okay, so how do we do this? I reviewed it in class. Well, no, I mean, I told you how to do it in class. I'm going to review the method we did in class because I think it's pretty elegant. So as we start, when we started, we described everything in terms of what this original observer O sees. So this is Carl relative to the origin, and this is A relative to the origin. But now I want to talk about what Carl sees. So that'll be Carl, A relative to Carl. And then I say, okay, we've got 3 vectors here. How are they related? There's always related in a plus addition way. So it's going to be VCO plus AC is equal to XAO. So that's how their position vectors are related in the 2 reference frames. And then I take the derivative of this expression. Velocity of Carl as seen by the origin plus the velocity of A relative to Carl is equal to the velocity of A relative to the origin. And the thing is, I know this term and I know this term, so I rearrange this. VAC is equal to VAO minus VCO. Carl's moving at 1 meter per second, so I'm going to subtract 1 meter per second for each of these. So the first one is 5 meters per second minus 1. The second one is minus 1. Minus 1. And the last one is 1. Minus 1. I guess I should write meters per seconds here. So 4 meters per second. Minus 2 meters per second. And 0. Oh, hey, look, we're probably in the 0 momentum reference frame. So these are the velocities before and after. Okay, according to Carl, how much kinetic energy has been converted into heat? And should we expect them to be the same value? Okay, so KE initial is going to be 1/2 times the mass of cart A, which is 4 and 8. Okay, so 4 times 4 squared plus 1/2 8 times minus 2 all squared. So that's 4 times 4 times 4 divided by 2 plus 2 times 8. 48 joules. KE final should be 0. So the change in kinetic energy, all that turns into heat, minus 48 joules. So we lost 48 joules to heat. Okay, so should these have been the same number? Yes. And this is actually kind of a fun bit because depending on your reference frame, you do a different amount of work. Depending on a reference frame, your kinetic energy might differ. But everybody, regardless of inertial reference frame, will agree on the amount of energy that turns into heat and the amount of energy that turns and the amount of energy that comes from potential, like change in heat, change in potential energy. Everybody's going to agree on those. So that's neat. Okay, Alain and Brenda trying to move a solid sled across a lake. Despite, now here's the thing. This question has some tricks in it. I know that you are wise, and I know that you're smart, and I know that you're brave. But do you read questions carefully? Okay, so and on this, actually, I'm gonna give a short breakdown on how the marker assigned grades, because there's I mean, controversy is the wrong thing, but some people have questions about it. So the first thing to note is, despite all the nice things people say about ice, this lake has rough patches. It's not easy to keep the sled moving. That means friction is not 0. Neat, huh? Okay, so Brenda's pulling the sled forward and Alain is pushing the sled behind. Let's list out all the forces. Free body diagram. All right, so there's gravity. There's a normal force. Friction points in this direction. All right, so here's the push from Alain, F push, and then Brenda pulls in that direction, F tension. All right, so the marker, when they did it, decided to take marks off if you didn't write that was 20 degrees. And it's a helpful thing to put there, so you should do it. Anyway, the marker took uniformly off marks for that, so I'm not going to question it as per my philosophy on the matter. But FYI, yeah, people lost a half mark if they didn't write that specific angle. All right, next part. Okay, so hold on. Determine all the components. Determine all the components of each force, and that means I want you to find the numbers for each one. And then write a list of all the forces in terms of their unit vectors, okay? So I want you to list the unit vectors for each force. Now, how do we do that? Before we go on, the marker was giving one of the 6 marks you can earn based on the process you used. So I'm going to break this down the way I've been doing most of these questions. The first question I ask myself is, what kind of motion is this? Constant velocity, constant acceleration, what's going on? Which direction is accelerating in? That kind of thing. The sled maintains constant velocity. So the first thing I note is that the acceleration is going to be 0. And F net, as a result, has to be 0. Why is that important? It's important because if you don't know this, you can't answer the rest of the questions. So the marker decided to take off 1 mark, or rather give 1 mark for having that. It's an intermediate step. He also taxed people for not writing their intermediate work. So if you just wrote your answers and didn't write fnet is equal to 0, he didn't give you a grade for it. The only way to get perfect grades is to show your work. Okay, so now let's break this down. F push. That is 100 newtons to the right. Yeah. 100 I hat. F tension, Brenda pulling, that's going to be 200 I hat plus 200 sine 20 j hat. All right, let's do the math here. 200 times cosine of 20. That's 188 I hat plus 200 sine 20. 68.4 j hat. All right, what else we got? We have gravity. That's minus 9.81 times 60. 588.6 newtons in the j hat direction. Now, I don't know the normal force. I know which direction it's pointing. And I don't know what the friction force is, but I know which direction it's pointing. Okay? So these are 2 things that I don't know off the top of my head. I haven't been given them. The rest can be found using vector analysis. Somebody just wrote the question, how do you determine the direction when it involves angles? Okay, Sherry Marie, I hear your question. I'm going to finish this problem, and I want you to elaborate on the question you're asking, and then I'll try to address it, okay? Alright, so how to finish this problem. The deal is that the net force isn't just from the angle. We know from the acceleration what the net force is. So from this, we know that all of these forces have to add up to 0. And in other words, friction force has to balance out all of the horizontal forces. The unknown normal force has to balance out all of the vertical forces. Okay, so I put them all together. So first the I hats. So it's going to be 0 is equal to, there's one of them, 100 plus 188 minus friction force. And then j hat. 0 is equal to 68.4 minus 588.6 plus little n. And these 2 tell us what the final forces are. 4 full marks. This is going to be 288 newtons. It's going to be 520 newtons. Okay. So that's what you need to get full marks. Last question. What's the coefficient of kinetic friction? Well, this is sliding friction. And that means it's related to how strong the normal force is, and it's always a constant magnitude. Its direction is from context, but the strength of it depends on how big the normal force is, and the coefficient of friction according to F is equal to mu sliding times n. So 288 is equal to mu s times 520. Mu s is equal to 0.55. All right, so that's that answer. Now, to go back to the live chat, Sherry Marie has asked, how do you determine the direction when it involves angles? And what she's talking about is this force, that calculation. Okay? This is a calculation that shows up in a lot of different things. We saw it on the first midterm as well. So how do you do it? I'm going to go down to the bottom here and just give a quick note on vector analysis. Sorry, I'm chasing this hair on my pad. All right. Vector decomposition. That's the name of the topic. The idea here is you got a vector. You have some basis. I hat, j hat. Okay. Sometimes you get a vector that's in the I hat direction, 3 meters long. Say. So then you would say v is equal to 3 I hat. Sometimes you have a vector that's just in the j direction. Call that u. Call this v. Say 7. So you'd say u is 7 units long in the minus j hat direction, which is a minus 7j hat. Okay? But more often than not, you get a situation with neither. So that's essentially the calculation we've been doing you saw me do that in this part, this part, this part, and this part, because the forces here align with j hat, I hat. Where did we define these? I said vectors I hat to the right and j hat up. Okay? So sometimes we draw it, sometimes you just spell it out, but these are the unit vectors. And like I said, more often than not, you get a vector that's a blend of the two. So what are we going to do in that case? Let's suppose that this is, okay, so this is the I hat direction. Let's suppose that it's 40 degrees to the I hat direction. How are we going to break this down? Well, the thing about vectors is that all vectors are made of other vectors through a process of either scaling them up or adding them together. And there's no bottom to this. It's just us saying, hey, all vectors are made up of other vectors. So this vector v is made up of a part that's parallel to I and a part that's parallel to j. So when I describe a vector, as I did up here, you'd usually do it in terms of its length and which direction it's pointing in, right? So I can't do it with this one specifically because this one isn't pointing in either of these directions in any kind of way. But if I decompose them in this right angle triangle, this one is in the I hat direction and this one is in the j hat direction. So all I need to do to describe these composing ones is I need to figure out what the length of it is. The nice thing about vectors is the length is, the magnitude of the vector is its length. So I can use trigonometry to find the length of this side, which is going to be 60 cosine 40 degrees, and this side, which is going to be 6 times sine of 40 degrees. .86 4.60. Okay. So now I know the length of each of these. This is 3.86 and this one's 4.60. So our vector is going to be this one, Vj plus Vi, and Vj is 3.86 in the j hat direction, and Vi is 4.60 in the I hat direction. And that's how we decompose them. That said, things can get a little bit more fun. I hat, j hat, things can get more fun if you get a vector, say, pointing in that direction. Let's say this is 7, and this angle here is 30 degrees. Okay? I can decompose it like a triangle just like before. 30 degrees, 7, so this side here is 7 times sine 30, and this side here is 7 times cosine of 30. So this side is 3.5. And this side is 6.06. But there's a thing here. This vector here is going by going to the left. I'll call that VI, and up, VJ. Maybe its name should be W. All right. So W is made up of 1 going to the left and 1 going up. Okay. We have to be careful. I mentioned this earlier. We see ourselves doing it, say, for this one. This one's a negative number because gravity points in the opposite direction of the j hat vector. So this is pointing to the left. It's in the opposite direction of the I hat vector. So the number is 606 minus I hat plus 3.5 times positive j hat. So this becomes minus 6.06 I hat plus 3.5 j hat. Does that make sense? In other words, what we're doing here is we're breaking down our mixed component vector into the two pure components, one going in the direction of I hat or parallel to I hat, one going in the direction of j hat, parallel to j hat. We use one of these triangles and trigonometry using the angle to figure out how long the sides of the triangle are. But then we need to consult our diagram to figure out which one's positive. So this one's positive because it's pointing in the j hat direction. This one's negative because it's pointing in the minus I hat direction. And then those signs show up in the final answer. So when we did this question, this was the decomposition we used. See, cosine and sine. I'm decomposing our 200 vector. This angle here is 20 degrees. I'm using trigonometry to find the length of this side and the length of that side. All right. All right, let's move on to textbook questions. We have a lot of them today, so buckle up. The nice thing about this Missouri text is that it puts a lot of things together all at once. The sad thing about it is that at the end of the term, when you can really cook and improvise and use all these ideas together in complicated ways, there's barely any time to see about how things are put together. So I thought we could use some practice in this one. Page 157, question 16. Okay, you are lifting up. Okay, so this is a choice of system question. We talked about this in class. I can't remember if I did this one next week. Okay, whatever. You're lifting a ball at constant velocity. When the system is the ball, is work done on the system? If so, by what agent? All right, well, here's me. Here's a ball. I'm lifting the ball in the air. Is work being done? Oh, V is equal to constant. Fun. Okay, so systems. What's the system? The system's just the ball. What are the forces? What are the external forces acting from something outside the system onto the system? There's gravity, and then there's the pushing force. Okay? So is it moving in the direction of these? Yes, it is. So yes, work is being done. By gravity and by my hand. We're both doing work. Everybody's doing work. It's the end of the term. Describe the potential energy of the system during the lift. There's no potential energy because there's no potential energy associated with the ball itself. If the system were the ball and the ground, then there'd be potential energy. But in this case, no. When the system comprises the ball and the earth, is work done on the system? Okay, so if it's the ball and the earth, what are external forces are there? There's the pushing force. Gravity an external force? No, because gravity is a force from the earth on the ball and from the ball on the earth. And both of those forces are internal forces, objects inside the system pushing the system. So in terms of our system, this one's the only external force. Of course, the ball is moving upwards. So yes, there is work. Yes, work. By me. I do all the work. You guys just sit and watch while I do all the work. It's not true. You guys work a lot. Okay. Okay, so describe how the potential energy of the ball or system changes during the lift. Does the potential energy increase? Yeah, potential energy increases. U increases as ball and earth get farther apart. Does that make sense? Yes, this is a pretty good final question. We should ask this question in the final. Okay, next. Oops. Maybe I'll switch to a different color. Next, it's question 25. Question 25 goes like this. A bicyclist pedals distance D at a constant speed on a level stretch of road. She then pedals up a hill and passes slowly over the top. As she coasts down the other side of the hill, she applies a brakes and comes to a stop at distance D past the top. Oh, this is asking for energy diagrams. We're not doing energy diagrams this term. We're not doing testable energy diagrams. But it's something we've talked briefly about, though. Okay. So let's draw two pictures. And then there. Same. This is before. Here's our bicyclist. Before and after. Yeah, that's what they look like. Okay, so what types of energy are there? Okay, first off, system. Let's go the bike, the person, the hill, the earth, the air. I don't know, that seems like everything. Useful. Okay, so what different types of energy are there? There's kinetic energy. So initially she's got a bunch of kinetic energy. She's pedaling up the hill, so I think that there's probably some chemical potential energy. She's got, like, she ate a sandwich, so she's got some calories to burn. What else is there? There's the gravitational potential energy, which is currently 0. There's heat, which is currently 0 because it's cold outside. What else is there? Any other potential energies? No. Okay. So, at the end, this is a closed system. Hooray! At the end, the kinetic energy is 0. She burnt all her calories going up the hill, so that's 0. She's hungry. Gravitational potential energy, that's bigger than it was before. It was even bigger than that once. And then all the rest of this junk goes into heat. Yeah, I mean, so she produced heat from her brakes. There's friction from the road. There's heat everywhere. Fun question. Next question. Oh, I'm tired. 26. In emergency braking, a certain car, is it, requires 7 meters to come to a stop from an initial speed of 10 meters per second. Use an argument based on work done on the car to determine the braking distance required if the car's initial speed is 30 meters per second. Oh, hey, this one's cute. Okay, so I don't know how much mass the car has, but when you turn on the brakes, that generates some force pushing in that direction. Static friction, to be honest. No, wait, sliding friction. Well, both, depending. Okay, so that means that it takes you a certain distance to come to a stop. They're telling us that it takes 7 meters to come to a stop, which is pretty good. And the initial speed is 10 meters per second. So, the next question goes, how far did it take to stop? Same car, I don't know what its mass is. And its initial velocity is 30 meters per second. D, until P is equal to 0. How do we do this question? Well, you could probably use kinematics if you felt like it. But, because the brakes are going to generate the same amount of acceleration. But we'll be using work. Here's the idea. We don't know how much friction force there is, but we do know that if the system is the car, then the car's change in kinetic energy is because work was done to it. And the work is done by the friction force. Okay. So dig it. This is going to be really sweet. All right. So what's the change in kinetic energy in this first case? Ke final minus Ke initial. The final kinetic energy is 0. The initial kinetic energy is 1/2 m10 squared. And I know that that's done by the work. Sorry, I know that that's work done by friction force. Friction force is in the opposite direction from the displacement. So it's going to be minus friction force times 7. This one now. Okay, so, whoa, geez, there's two things I don't know. I don't know what the mass is, and I don't know what the friction force is. But never you mind. Kef minus Kei. Alright, so, in the second one, final kinetic energy 0, mass 30 squared is equal to minus F friction times D. Okay, so how do I solve this question? There's 2 equations and 3 unknowns, right? But wait, hold on. You can do something really fun here. I'm going to take the mass and I'm going to divide both sides by the mass. So this becomes minus 1/2 times 10 squared is equal to minus friction force divided by mass times 7. And then minus 1/2, 30 squared is equal to minus friction force over mass times D. Sweet. So here's the idea. That whole unknown thing, that's it's going to be the same value in both. So whatever it is, it's going to be 50 divided by 7. 7.14. Plug that in here. So 1/2 times 30 squared is equal to 7.14 times D. D is equal to 30 times 30 divided by 2 divided by 7.14. 63 meters. Whoa, that's far. Why is that so much farther? Why is it so much farther? Can you guess? The answer is predictable. It is much farther, but dig it. Let's compare their kinetic energies. The kinetic energy for the original one is 1/2 mass 10 squared. The second one is 1/2 mass 30 squared, which you can rewrite as 9 times 1/2 mass 10 squared. You dig what I'm saying? In this case, there's 9 times more kinetic energy than in this case, which is bonkers. There's 9 times more kinetic energy. The friction force is eating away at the kinetic energy by doing work at it, but it can only do it so much per meter. So it takes 9 times the distance to stop. 9 times the distance to eat away at that kinetic energy. Isn't that bonkers? That's pretty fun. Makes sense. Okay, next question. What is that, 26? Oh, 26. 29. Feeling fine. Your 20-kilogram child runs up the amusement park wave slide shown in figure 9.29. Yeah, let me copy this down. I just found out that there used to be like this amusement park halfway between here and Vernon. It was called like the Magic Castle or the Enchanted Forest or something like that. Oh man. Apparently they made one of these big slides. It was run by 2 school teachers in the summertime. It's right up the road from the bunny sanctuary. It's not there anymore. Okay. A 20-kilogram child runs from the amusement park wave slide shown in this figure. When she's nearly at the top of the first hump, which is 9.9 meters above the water, she flops down and slides over the top of the hump at 1.5 meters per second. Oh wait, hold on. She slides down the other side of the hump and then up the slide until she reverses motion at a height of 0.95 meters above the water. What is the increase in thermal energy of the child and the slide due sliding from the top of the hump to the top of her motion? What the heck question is this? Hey, who wants an example of a question that doesn't make any friggin' sense? Look at chapter 9, question 29. Oh, hold on. I think I've got it. The kid's not coming down the slides. When they say that she ran to the top, she doesn't mean that they went the appropriate distance up the slide. It means that your kid is being super bad and going this way up the slide. God, what an evil child. Okay, so she's nearly top of the first hump. That's why they call this one the first hump. Bad child. Her velocity is that way. 1.5 meters per second. She slides down over the side of the hump and then up the slide until she reverses motion at that height. Oh, geez. So she goes down and up. Okay. So the question here is how much heat generated. And it's not that tricky. The deal here is you got to define a system, right? System. Bad child. Slide. Earth. Uncomfortable bystander. Surly teenage employee. Both these people are up here. So here's the surly teenage employee sounding, get off the slide. Get off, eh? And then here's the bystander. Like, how could that parent be so irresponsible? Okay. Right. So what kind of energy is there in the system? This is going to be a closed system because we listed everything in the world. So there's going to be thermal energy. And there's going to be gravitational potential energy. And there's going to be kinetic energy. And you know at this point V is equal to 0. Okay, so the idea here is that E total is going to be the same before and after. So before, that's this moment. After is when you're there. Final, initial. All right, so how much thermal energy is there initially? 0, I guess. Who cares? What we care about is the change in thermal energy. Okay, so initial gravitational potential energy. Let's see. We'll go off the ground. So it should be 20 kilograms the mass times 9.81 times 0.9. And the kinetic energy, 1/2 times 20 times 1.5 all squared. So it's 199 joules, which is approximately what they'll have to pay to get back into the park after they've been banned. Thermal energy, I don't know what it is. I'll write a T. The gravitational potential energy is 20 times 9.81 times 0.95. And the kinetic energy is 0 times 20 times 0 squared. So T plus 186.4 is equal to 199. So the thermal energy is going to be 12.6 joules. So that's fun, right? All right, next question. 29, 51. Wait, 43, 51? What's the thing? Oh, 51 and 43. Fine. 51 goes like this. A 6 kilogram bowling ball is held 1 centimeter above a mattress and then released from rest, allowing it to fall, sinking into the mattress. Model the mattress as a single spring with spring constant 500 newtons per meter. Calculate the ball's kinetic energy, gravitational potential energy of the Earth system, and elastic potential energy at the following compressions. What's the maximum compression of the mattress? Okay, so this is an energy question, and we're using the formula for the spring potential energy that we saw in class. So I'm going to draw the initial setup, which is going to define how much total energy we have. Okay. So this distance here is initially 10 millimeters, 0.01 meters. Okay, and this is a 6 kilogram. So now it's been compressed. Oh, geez, that looks bad. Sorry, I was looking at the page while I was drawing. It's been compressed a little bit. And then it's been compressed more. And then it's been compressed more. And then it's been compressed more. Okay. So, there's a reason I drew them all in the same diagram, which is that I want to talk about the gravitational potential energy. So if this is the uncompressed spring height, can I move this around? No, I can't. No, I can't do it. Maybe like this. There. Okay. So, what types of energy are there here? There's kinetic energy, there's gravitational potential energy, and there's spring potential energy. Okay? And the total is going to be the same for each of these. So, the idea being that in each of these situations, we have a sense of the position of the ball. That's going to tell you the gravitational potential energy. And we have a sense of how compressed the spring is, and that's going to tell us the spring potential energy. And then we're going to use the total energy to figure out what the missing kinetic energy is. Does that make sense? Okay, so let's start. To do this, note, first off, they haven't told us how high the spring is off the ground, and they haven't told us how high the bed is off the ground. We talked when we were introducing the idea of gravitational potential energy about how when we define it, what we get is a sense of how the GPE changes depending on the height, not some absolute scale. And what that means is we can make the gravitational potential energy 0 any dang place we want. So I'm going to make it 0 at the uncompressed height. I'm going to call that y is equal to 0. Okay. So initially, so the KE is equal to 0. The GPE is equal to 6 times 9.81 times let's see, this initial height here is 0.01 meters. And the spring potential energy is 0 because it hasn't been squished at all. So let's do it. This system has 0.05886 joules. Okay, now the fun part. Whenever we're doing this calculation, we're talking about the height of the bowling ball. To calculate the gravitational potential energy, I'm going to calculate the height of the bowling ball above or below this y is equal to 0 line. So in the first one, let's see, it says, what does it say? In the first one, it's y, the height of the bottom is at y is equal to minus 0.05 meters. And in the second one, it's, this height is y is equal to minus 0.1 meters. And at this height, it's y is equal to minus 0.15 meters. And in this one, it's y is equal to 0.2 meters minus. This will give me a negative gravitational potential energy, but that doesn't matter. Potential energy is a relative thing, so all we really care about is how it changes, and the gravitational potential energy decreases the farther down you go, which is normal. Alright, so in this one here, kinetic energy is unknown. The gravitational potential energy is going to be 6 times 9.81 times minus 0.05. And the spring potential energy is 1/2 times 500 times the distance it's been squished, which is 0.05 all squared. So now I add these up. It's Ke plus 250 times 0.05 times 0.05 minus 2.318 joules. So these two have to add together to give me this. So the kinetic energy is going to be that. .376 joules. Fun. You do this over and over again. Let's just do this one. So I'm kind of out of space. So the kinetic energy plus the gravitational potential energy, 609.81 times minus 0.2 plus 1/2 times 500 times 2 all squared. So that's Ke plus minus 1.772, and these two have to add up to make that. So the kinetic energy is equal to 1.83 joules. What to note here? Note here that the kinetic energy here is pretty big. Why is it pretty big? It's because gravity's done work on the ball. I guess the gravitational potential energy has given the ball energy. And as it descends, the gravitational potential energy continues to give the ball energy. That said, the spring is doing work on the ball. And the farther down the ball goes, the harder the spring pushes. So we're already at the point where the spring is slowing the ball down. now the question here is, what's the maximum compression of the mattress? In other words, how far down does it go? Ke plus gravitational potential energy plus spring potential energy. I want to know where the kinetic energy is going to be 0, because that's where the ball has briefly stopped moving, stopped going down, and started going up. Okay. Gravitational potential energy at this position, note how we're doing it, right? So we're going, here's your spring, here's your ball. It's going to be some height, y, below our y is equal to 0 line. So gravitational potential energy is 6, its mass 9.81 times minus y. And the spring potential energy is 1/2 times 500 times minus y all squared. So all I have to do is solve this quadratic equation. So this is minus 58.9 y plus 250 y squared is equal to 0.05886. And you solve this, and then y gives you maximum compression. Yeah, so you solve it using the quadratic formula. Want to see me solve it using maple? Sure you do. Hold on, booting up maple. Let's see. Window capture. And hold on. But I can't. Let's see. There we go. Haha, look, it's maple. You seeing this? Is this fun? Okay, so solve. Maple, solve it for me. Minus 58.9 times y plus 250 times y squared minus 0.05886 is equal to 0. Y. All right, there's my answer. Boop. Boop. So according to Maple, the answer is a height some sig figs are probably going to make most of these go away. 7. All right, so that's how far the thing is squished away from the vertical. Does that make sense? Yeah. If you want to, you can use the quadratic formula, but if you're lazy, you can use maple. Okay, so that's question 51. Now question 43. Oh, give me a rest. You fire a bullet, inertia m, into a block shown in this picture, the bullet is initially traveling at speed v, and the inertia of the block is 4m. The surface on which the block sits is rough, and the spring has constant k. The bullet becomes embedded in the block. If the spring compresses a maximum distance d, what's the magnitude of the frictional force exerted by the surface on the block while the block is moving? Can you believe that question? It's not as weird as it looks, but it's pretty weird. Okay, hold on. Spring. Block. This block has 4m. Here's your bullet. It has mass m, v, speed v. Okay, so here's the idea. The bullet becomes lodged in the block. And that gives this guy some velocity. There's two forces acting on the block. There's a spring force as it compresses the spring, and a friction force. Okay. So the thing manages to squish the spring a certain distance. Let's go here. That distance is little d. And I want to know how big this friction force is. Okay, you ready? We do it with systems and energy. So the system is the system here is the block, the bullet, and the spring. And what that does is it takes this force out of the equation. Now the only external force is the friction force. Okay? So, initially, say at this moment, the system has two different types of energy. It's not a closed system, but it has kinetic energy and spring potential energy. At this moment here, the kinetic energy is equal to 0. You can have a value for the spring potential energy, which is 1/2 kd squared. So the deal is the change in total energy between these two is due to work minus the friction force times the distance it travels. Oh wait, hold on. I said that wrong. Nope. So, E total final minus E total initial is going to be equal to this work done. And that's the connection between all these things. So to do this, we need to figure out how much inertial kinetic energy it has. We know that there's 0 spring potential energy, but I don't know what the kinetic energy is. How do I figure that out? Well, it's not the total energy in the system here, because as the bullet gets lodged inside, some energy is going to dissipate. We need to use momentum. So the initial momentum is mv plus 4m times 0, because it's not moving, so it's just mv. The final momentum is going to be, I'll call it w. It's going to be 5m times w, and that's going to be mv. So w, the speed of the block with the bullet in it, is v over 5. And that means the kinetic energy initially is 1/2 times 5m times v over 5 all squared. And now I have an expression for the energy before and the energy after. 1/2 kd squared minus the initial energy, which is going to be 1/2 times m over 5 v squared is equal to minus F friction dot D. And then you rearrange this. F friction is equal to a minus sign. Minus, plus, plus. Okay. And then I'm going to divide by D. So this is going to be m over 10 times dv squared minus 1/2 kd. Fun, huh? I love derivation questions. They're so much fun. Okay, that's it for that particular section. Let's mosey on down to page 183 and start the next batch of questions. Oh my god, it's been an hour and 16 minutes. So this is page 183, question 65. 65 goes like this. If the angle between vectors A and B is 165 degrees, let's draw these. Here's A, here's B, and this angle is 165 degrees. If A is 3 meters, and B is 2.5 meters, calculate A dot B. Oh, hey, look, it's 3 times 2.5 times cosine 165. Should this be a positive or negative number? It should be negative because they're counter-aligning. They're pointing in opposite directions. 3 times 2. Okay, so cosine 165. I just want you to see something here. 2 times... No, come on, hand, just once. Minus 0.966. You got a negative sign because they're counter-aligned. You don't have to insert it by hand anymore when you're using these formulas. So it's minus 7.24. Ta-da! Now it's question 68. Force 50 I hat plus 12 j hat is exerted on a particle that moves along the x-axis from delta x. It moves from, so it's x final minus x initial. So the final position is minus 5 I hat and minus 1 I hat. So that's minus 6 I hat. Determine the work. So we can use this formula if you want, but you need to know the angle, so that's annoying. So instead we're going to use the formula where I multiply these components together and multiply this with this. So it's, hold on. I'm multiplying these together, the I hat components together and the j hat components. So it's 50 times minus 6 plus 12 times 0. So it's minus 300 joules. What's the angle between them? Okay, so to figure out the angle between them, how you do it is you draw out the thing. So there's delta x, that's 6 meters. And then you draw the force, that's this guy. So if I knew how long this was, then F dot delta x would be 6 times the length of this line times cosine theta. And we know that if we did that, it would equal minus 300. The thing that goes here is the magnitude of the force. So to figure out the magnitude of the force, I just use Pythagoras. So the magnitude of the force is going to be square root 550 squared plus 12 squared. $51.4. All right, so 308.5 times cosine theta is equal to minus 300. And you rearrange these and you use the arc cosine function, so it's minus 300 divided by answer. 166.5 degrees. That's not a degree sign. Alright, so that's fun. You'll see a little bit more of that if you take a linear algebra class. It's not rocket science. Question 70. Calculate C dot B minus A if A is equal to 3I hat plus 2J hat and B is equal to 1I hat minus 1J hat and C is equal to 2I hat plus 2J hat. Alright, so this is a simple arithmetic question. It's kind of an orders of operations question. You do the parentheses first, and then you do everything outside the parentheses after. B minus A is going to be, I'm going to subtract them. So it's 1 minus 3. Okay, 1 minus 3 I hat plus minus 1 minus 2 J hat. So that's minus 2 I hat minus 3 J hat. And I'm going to take the dot product between this and 2I hat plus 2J hat. So C dot B minus A, dotting these two vectors together, you get that times that, so it's minus 2 times 2 plus minus 3 times 2. So that's minus 4 plus minus 6 is equal to minus 10. There you go. That's how to do that question. Never say I never taught you nothing. You're playing with a toy in a I gotta drink some water. Okay. You're playing with a toy in which a marble launched by a spring rolls across a track full of loop-de-loops and curves with almost no energy dissipated. Oh, congratulations. You want the marble to have speed of 0.7 meters per second when it arrives at the top of a loop that's 0.3 meters higher than the marble's position when you launch it. All right, so you got your marble launcher. Pachoo! And it goes around like that. So what they're saying is this distance here is 0.3 meters. And you want the marble's speed here to be 0.7 meters per second. And then maybe you want your work to be in a part of a page where it's not overlapping with some previous jerk's work. Alright, so how do we do this? Okay, fun. So here's the thing. I'm not sure what this has to do with work. You can do this question really easily with potential energy. So I guess I'll do it with work. Sure, why not? So the system is the marble. The normal force is always perpendicular to the motion, so it's not going to do any work. So the only force that does work is from gravity. So the force from gravity is minus 9.81 times the unknown mass. And the displacement is going to be, okay, so it's in the j hat direction, and so 0 I hat. And the displacement is starting from here, going to here, you go up by 0.3 meters. 0.3 j hat plus 0 I hat. So the work done by gravity is going to be F dot delta x. You just multiply the components together. Minus 2.94 times the mass. Okay. So this shows how much energy our system has lost. Kinetic energy initial is going to be, I don't know, V squared. Kinetic energy final is going to be 1/2 times 0.7 all squared times m. So 0.7 times 0.7 divided by 2. 0.245 m. And then I put it all together. Delta Ke is equal to the work. So 0.245 times the mass minus 1/2 the unknown Vi times the mass is equal to minus 2.94 times the mass. All right, and then you factor out the mass. Boop, 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 boop. So Vi squared is equal to 0.245 plus 2.94 times 2, 6.37, and Vi is equal to the square root of that, 2.52 meters per second. Yep. Okay, so that has to be the initial speed. Part B says if the spring constant is 13 newtons per meters and the mass is 0.005 kilograms, how much potential energy in a spring do you need? Okay, so kinetic energy, if the system is the spring and the ball, kinetic energy plus spring potential energy, Ke plus spring potential energy. The system is arguably closed, so it's going to be the same amount. The spring potential energy at the end is 0. The kinetic energy, 2.52 times 0.52 times 0.005 divided by 2, 0.0159, and there's 0 kinetic energy at the start, so it's all going to be spring potential energy. 1/2 times 13 times the delta x, how far it's been squished. And so delta x squared is going to be equal to 159 times 2 divided by 13. No. 0.0159 times 2 divided by 13. 0.0024, and delta x is equal to 0.0494, which is 4.9 centimeters. You got to pull it back 4.9 centimeters. Oh, I'm tired. All right, what was that? 71. Well, 73. Hooray! More questions. Can't wait to do more of these questions. A 20-kilogram boy slides down a smooth, snow-covered hill on a plastic disc. The hill is at a 10-degree angle to the horizontal, and the slope is 50 meters long. The boy starts from rest. What's the speed at the bottom of the hill? Okay. So, like I said, this is another question you can do really easy with gravitational potential energy, but let's use work. So if the system is the, all right, so the displacement, that's that, delta x vector. So if the system is the boy and sled alone, what are the forces on it? There's going to be the normal force from the hill and gravity. This force is perpendicular to delta x, so no work will be done. This force, though, it's not perpendicular. It's, let's see, its mass is 9.81 times kid's mass, 20. 196.2 newtons straight down. Okay, so here's the fun part. So here's the force, 196.2 newtons, and here's the displacement, 50 degrees, and this angle here is 10, no, it's 50 meters. Then this angle here has got to be 80 degrees, and so F dot delta x is 196.2 times 50 times cosine of 80. $1703 joules. Right, and so his final kinetic energy, so this is the work done by gravity. So the final kinetic energy is going to be the initial kinetic energy plus the work. So the final kinetic energy is going to be 1703, and so the final velocity is going to be divided by the mass times 2 square root 13 meters per second, which is tremendously fast. His sister then hauls him and the disc from the bottom of the hill . 50 times sine 10 times 9.81 times 20. Yeah. Okay, sure. His sister then hauls him and the disc from the bottom to the top by means of the rope attached to the disc. Okay, they're going up the hill. From the bottom to the top by means of, okay, a rope attached to the disc. What average force must she exert on the rope if the boy is going 0.5 meters per second by the time he reaches the top? Okay, So presumably you're going to start at v is equal to 0. Okay. So the system, again, let's make it a it's just the Boyne disk. Okay. So what forces are acting on it? There's gravity, there is the normal force, and then there's going to be a tension force pulling the kid up. KE initial is 0. We want to keep track of the work all these forces are doing. Normal force does 0 work because it's perpendicular. The tension force is going to be the tension force, the work done by the tension force. It's going to be the tension force times 50 because they're in the same direction. And the work done by gravity, it's going to be, I mean, we don't need to reinvent the cow. It's this much, but minus, because they're in opposite directions now. So, we know kinetic energy final is 1/2 times the mass, 20 times its final velocity, 0.5 meters per second squared. .5 joules. Okay, so delta KE is equal to the total work done. So it's going to be 2.5 minus 0 added to the work done. T times 50. Minus 1703 joules. And you can rearrange this and solve for T. 2.5 plus 1703 divided by 50. 34 newtons. She has to pull 34 newtons up the slope. All right. Oh, 76. I'm waiting fast here. 76 goes starting for, oh, it's a 3-ball question. Why do I choose these? I'm always like, hey, we should have a fun question. And then when I do it, I'm like, oh, I'm tired, and then I have to do a 3-ball question. All right, starting from rest, an intern pushes a 45-kilogram gurney. Do you know what a gurney is? It's the thing they push grannies around on. 40 meters down the hall with constant force 80 newtons directed downward at an angle 35 degrees with respect to the horizontal. That way. What's the work done by the intern on the gurney over the 15-meter trip? Well, that's delta x. So it's F dot delta x. Let's draw them. This one is 15, and the other one is 80 newtons. At an angle 35 degrees. So this is going to be 15 times 80 times cosine 35. .983 joules of work. Oh, they're working hard. How fast is the gurney going when it's moved 15 meters? That's A. B, how fast? K final is equal to K initial plus the work. Let's assume the initial kinetic energy is 0. All right, so that's the final kinetic energy. 1/2. It's a 45-kilogram gurney. Final velocity is 6.6 meters per second. Yikes. This is a bad intern. Okay, how much time elapses during the 15-minute journey? Ignore friction. There's probably a couple fun ways to do this. Let's figure out what the acceleration is. What are the forces? There's gravity. There's the normal force. And there's this pushing force. I only really care... Okay. So that's going to be 80 times cosine 35. 65 I hat minus 46 j hat. All right, so before I go too farther, I'm getting tired, so I don't want to do too much work. That and this are all going to balance out. So the F net in the is going to be 66.5 I hat newtons. And oh, the door's knocking.
Hi.
Hi.
Are you busy?
Yes.
Okay.
What can I do for
I just
you?
had a quick question for you.
What is it?
I'm in Jake's physics class, and I'm exempt from the tutorials because I took physics already. I was wondering if I could. Is there any way I could get the tutorials for my study material for final?
I think Jake has them. You asked Jake for them?
I did. I didn't give it for me to you.
Oh, okay. Tell Jake I'll email them to him.
Okay.
For them, okay.
Awesome. Thank you.
Bye bye. All right. Where were we? Oh yeah. Okay. So I know all the forces are balancing out. That's what the normal force does. So all that's left is this force, and so the acceleration is going to be divide that by the mass, which is 45 kilograms. So 1.47 meters per second I hat. You know its final velocity is that. Its initial velocity is 0. So we can use kinematics. 6.6 is equal to 0 plus 1.47 times t. 6.6 divided by 1.47 is 4.49 seconds. That's how long they're pushing it for. All right. That's 7.6. Now let's do 90. A man exerts a constant force to pull a 50-kilogram box across the floor at constant speed. He exerts this force by attaching a rope to the box and pulling so the rope makes a constant angle 36.9 degrees above the horizontal. The coefficient of kinetic friction on the box floor interface is 0.1. What's the work done by the man as he moves the box? 10 meters. Huh. This question looks like there's more to it. Okay, so I'm going to just sketch out what's going on. Here's your floor. Here's the guy. Pulling on the box. It's hard life. And oh, it's funner than that. Okay, well, I guess I can keep going. Because you don't know how hard he's pulling. But you know that this angle is 36.9 degrees. So, what forces are there on the box? There is gravity. What is the box mass? 50 kilograms. There's gravity. There's a tension force. There is the normal force. And there's friction. And the deal is that all of these are going to balance out. Let's take it another way. What's the acceleration? It's going to be 0 because we know we're going at constant velocity. F net is therefore 0 because we know we're going at constant velocity. And now we just have to list out all these forces. Fg, gravity, is 50 times 9.81. That's minus 491 joules. The tension force, I don't know what it is, but F cosine 36.9 I hat sine 36.9 j hat. I don't know how big the normal force is, but I do know it's in the j hat direction. And I don't know how big the friction force is, but I do know it's in the minus I hat direction. And I do know that its value is related to the normal force, which I don't know. So I write it down as mu is 0.1 times the normal force strength I hat. So there's a lot of things I don't know here, but I do know that when I add them all up, you get 0. That's the key thing. So let's do it. The I hat direction. So 0 is, all right, now I'll just add up all of the terms here that have I hats. T cosine 36.9 minus 0.1 times n. And j, add those up in 0, minus 491 plus t times sine 36.9 plus little n. Hey, 2 equations, 2 unknowns. Hooray. Okay, so I'm going to just solve them as a set of equations. N is equal to 7.8.0 times t, and then 0 is equal to 491 plus 36.9. So it's 491 is equal to 8.6 times t, whatever t is. $57 newtons. All right. So you know how hard the force is that he's pulling with? And you know that this angle is, and you know that he's gone 10 meters. And you know this angle here is 36.9 degrees. So the work he does is 57 times 10 times cosine 36.9. 4, 5, 6 joules. Let's see if anybody's watching. Oh, one person's watching. Hello. All right, 91. Oh gosh, can it end? Can it end yet? The questions are endless. I swear I've done more practice questions than you guys have this term. An inclined plane that makes an angle of 30 degrees to the horizontal is a spring with spring constant 4,500 newtons at the bottom, and a 2 kilogram block released near the top of the plane moves down the plane and compresses the spring a maximum of 0.024 meters from its relaxed length. Ignoring any frictional effects, calculate the distance the leading edge of the block travels from the instant the block is released to the instant it briefly stops on the compressed spring. Okay. Now suppose there's friction between the block and the surface of the plane. If the block is again placed somewhere on the plane and allowed to slide down and compress the spring by the same distance, how far does the leading edge of the block travel now? Oh God. I'm tired. All right, witness me. So this is a 2.2 kilogram brick. And it moves down and it compresses spring. So the spring has compressed a distance that distance. How far has the block travels from the instant it's released until it compresses it? All right, so how far does the brick go? So here's its initial position. Here's its final position. How far is it between these two? Dig this clever use of stuff. What I'm going to use is the system is the spring and the brick. I should use work here. Shouldn't I use work? Oh, fudge it. I'm just going to not use work. And the earth. And the other stuff, the table. All right, everything's in the system. That means I can use gravitational potential energy. All right, so what I'm going to do is I'm going to say here, at this height, that height where its velocity is 0, at that height, that's y is equal to 0. Okay? So it's a closed system, and they said there's no friction. So we don't need to worry about anything turning into heat. What kind of energy is there? There's kinetic energy, there's spring potential energy, and there's gravitational potential energy. Initially, I'm going to switch them around. At this time here, the gravitational potential energy is 0, measuring from the bottom corner of this brick. The kinetic energy is 0, and the spring potential energy is 1/2 times, it's huge, 4500 times 0.024. I'll square it. Let me clean that up. Plus 0 is equal to 1.296 joules. The system doesn't have many joules. Okay, so now let's talk about when it's here. What's its kinetic energy? 0. How squished is the spring initially? It's not squished at all. So everything's in the gravitational potential energy. Mass 9.81 times 2.2 times this distance, that height h. Okay? What is h? Oh, geez. 9.81 times 2.2 is equal to 21.5. Oh, come on. 21.58 times the height, 1.296. So the height is equal to 0.06 meters. And then now I don't want to know what this distance is, but I have the angle of the thing. I know that this is a 30-degree angle. So that's 30, and this is 0.06, and that's D. So sine of 30 is equal to 0.06 divided by d. D has to be equal to 0.12 meters. So it started 12 centimeters up the slope. All right. Suppose there's friction between the block and the surface of the plane. Oh, jeez. Kinetic friction given. If the block is placed somewhere on the plane and then it squishes down, how far does the leading edge of the block travel now? Okay. To do this question, I'm literally going to do the same thing except for one difference. I want to take advantage of work. Because I know that friction's going to take energy away. So I want to make that work. I want to make the friction force do work, which means that it can't be in the system, which means that I have to take the table out of the system. So this is 0.024. I'm going to make this height again, measuring from the bottom, y is equal to 0. Okay, so system. It's going to be the brick, the earth, the spring. Not the table. So, what forces does my brick feel? Does my system feel, rather? The force, the normal force, and the friction force, which will push in that way. So I need to figure out how big the normal force is. Because once I figure out the normal force, I can figure out the friction force. Okay, no, mu times n. So, before I do all that, I have to do a free body diagram analysis of this thing. No, hold on, someone's at the door. Ah, God. Hey, what's up? Come back tomorrow.
Okay, sorry.
Alright, where was I? Oh yeah, normal force and gravity. So what I have to do is you tilt the axes. J hat that way, I hat that way. F normal is somewhere in the J hat. And friction is somewhere in the I hat. And F gravity is, most importantly, so it's 2.2 kilograms, right? 9.81, so it's 21.6 newtons. And you know that this angle here is 60 degrees. If you want to know what I'm doing, we did a lot of this at the start of the term. Tilting axes. So this will be 10.8 I hat plus, no, it's going to be minus J hat direction. Minus 21.6 times sine of 60 18.7 J hat. And then you add them together, and the N has to be 18.7 newtons. Alright, that's the thing to know. Back up here. Normal force strength, 18.7. And so the friction force is going to be, pointed up the slope, 1.87 newtons. All right, time to get to work. This is the distance that I'm trying to find. It's the distance, wait, hold on, there's the distance I'm trying to find. It's the direction and thing the thing traveled. Okay? So, again, kinetic energy final. It has three different types of energy. There's kinetic energy and gravitational potential energy. And I don't mean kinetic energy, I just mean energy. Gravitational potential energy and spring potential energy. How much kinetic energy does it have at the end? 0. How much gravitational potential? 0. How much spring potential energy? I already calculated this. It's 1.296 joules. Okay. How much energy does it have initially? The kinetic energy is 0. Gravitational potential energy, I don't know what that is, but I can write it in terms of this D term, right? So it's going to be, the mass is 2.2, 9.81 times the height, which is D times sine of 30 degrees. Because you know this 30 degrees. We've seen it over and over. All right, and the spring potential energy is 0. Here's the fun part. In this question, these two values aren't the same. They were before because the system wasn't dissipative, but now the system is dissipative. And so the work friction's doing is taking energy out of the system. So E final minus E initial is going to be equal to the work done. The force of friction points up and the motion points down. So the work is going to be minus 1.87, that's the force of friction, times the distance it traveled. You got it? Starting to get it now? So the final energy is 1.296 plus, I'm going to multiply all these things together so it's just one number. 2.2 times 9.81 times sine of 30. So this is 10.8 times D is equal to minus 1.87 times D. And now we can rearrange it. 1.296 oh, sorry. It's supposed to be a minus sign. Minus sign. Okay. So it's 10.8 minus 1.87. So it's going to be 8.93 times D. So D is equal to 1.296 divided by 8.93. Higher than it originally started. Why is it higher than it originally started? It's higher than it's originally started because it needs more initial gravitational potential energy to squish the spring the same distance, because it needs more energy to start with because some of that energy is going into heat. You dig it? Okay. 9-7. I'm almost at the end of this long assignment. Not even assignment. Okay, so a sport car skids to a stop, leaving skid marks 290 meters long. The coefficient between the kinetic friction between the tires and the pavements is 0.5. How fast was the car going before the skid? That's fun. All right, here's your car. It's got initial velocity. Hits the brakes. It's force pushing that way. At the end, it stops. So we have to start by doing kind of an analysis. I've done it. You do pretty much the same thing as here. So the friction force is going to be 9.81 times the mass of the car times the coefficient of friction. Hey, how come the normal force is mg? I thought you said it's never mg. I said that the normal force doesn't need to be mg. It is sometimes. What do you think you learned that? So it is this time. How do I know? I did the force analysis in my head. The gravity and the normal force have to balance. So. All right, so that's the friction force. And how far does it take to stop? 290 meters. What does that mean on this diagram? That means the distance between here and here is 290 meters. Okay? So that means the work done by the friction force is minus 290 times 9.81 times m times 0.5, which is minus 1422 times m. So that's the energy taken out of the system. Kinetic energy final minus kinetic energy initial. Okay, so here's the fun part. Final kinetic energy is 0. Initial kinetic energy is 1/2 mv squared. I don't know how big v is. But these m's cancel out. And you get 53 meters per second. That's how fast the car was going before the skid. Have a nice day. That's it for online office hours. Today, only 2 hours long. That's right, I only did 2 hours of questions for you to watch. Have a nice day.